NEC Section 300.5 requires the minimum burial depth for underground feeder cables to be 80 inches. In areas where physical damage is unlikely, for example, under a slab or pavement, the minimum depth can be reduced to 6 inches. The grounding requirements for a remote subpanel are the same as for any subpanel in a building. Install a grounding electrode system consisting of a ground rod, buried pipe, or plate electrode. Connect the grounding electrode to the panel enclosure using a grounding conductor of the appropriate size. There are other specific requirements to consider as well. Firstly, the underground conduit for the feeder cable should not exceed 10 feet in length. Secondly, use only approved connectors specifically designed for underground use. Thirdly, all electrical connections in the remote panel must be watertight. Fourthly, the remote panel should be installed in a moisture-proof enclosure to prevent condensation and moisture buildup. Fifthly, provide adequate ventilation in the remote panel to prevent overheating. Sixthly, clearly label the remote panel as such and indicate the location of the main service panel. Understanding these elements will help ensure safe and code-compliant remote subpanel installation. Let's delve into these aspects in greater detail, starting with the underground feeder cable depth. The NEC, or National Electrical Code, provides specific guidelines for burying electrical cables to ensure safety and prevent damage. For underground feeder cables, a minimum burial depth of 18 inches is typically required. This depth helps protect the cable from physical damage that could occur from digging, landscaping, or other activities. However, there are exceptions to this rule. In areas where physical damage is unlikely, such as under a concrete slab or pavement, the minimum burial depth can be reduced to 6 inches. This exception recognizes that the concrete or pavement provides an additional layer of protection for the cable. When determining the appropriate burial depth, it's crucial to consider the specific conditions of the site. Factors such as soil type, local climate, and potential for future digging or construction should be taken into account. It's always best to err on the side of caution and bury the cable deeper if there is any doubt about the potential for damage. Moving on to grounding for the remote panel, proper grounding is essential for electrical safety. The grounding requirements for a remote subpanel are similar to those for any subpanel within a building. The primary goal of grounding is to provide a low impedance path for fault current to return to the source, allowing the overcurrent protection device, such as a circuit breaker or fuse, to trip and energize the circuit. This helps prevent electrical shock and minimize the risk of fire. To establish a proper grounding system, install a grounding electrode system at the remote panel. This system typically consists of a ground rod, buried pipe, or plate electrode. The grounding electrode should be installed in accordance with NEC requirements, which specify the size and type of electrode, as well as the depth and location of installation. Once the grounding electrode is in place, connect it to the panel enclosure using a grounding conductor of the appropriate size. The size of the grounding conductor is determined by the size of the feeder conductor supplying the subpanel. The grounding conductor should be connected to the grounding busbar within the subpanel enclosure. In addition to the grounding electrode system, it's also important to ensure that the neutral conductor is properly isolated to the subpanel. The neutral conductor should only be connected to the grounding busbar at the main service panel. At the subpanel, the neutral conductor should be isolated from the enclosure in the grounding busbar. This prevents objectionable current from flowing on the grounding conductors. Let's now explore other specific requirements for remote subpanel installations. Firstly, the length of the underground conduit for the feeder cable should not exceed 10 feet. This limitation is intended to minimize the risk of condensation and moisture buildup within the conduit. When underground conduit runs are excessively long, temperature differences between the inside and outside of the conduit can cause condensation to form. This moisture can then damage the conductors and other electrical components. To prevent this issue, the NEC limits the length of underground conduit runs to 10 feet. If a longer run is necessary, consider using direct burial cable instead of conduit. Secondly, when making connections in underground applications, it's crucial to use only approved connectors specifically designed for underground use. These connectors are designed to withstand the harsh conditions of underground environments, including moisture, corrosion, and physical stress. Standard connectors are not suitable for underground use, as they can corrode and fail over time. Underground connectors are typically made of corrosion-resistant materials such as copper or stainless steel, and they are designed to provide a watertight seal. When installing underground connectors, follow the manufacturer's instructions carefully to ensure a proper and reliable connection. Thirdly, all electrical connections in the remote panel must be watertight. This is essential to prevent moisture from entering the connections and causing corrosion or electrical faults. Watertight connections can be achieved by using appropriate connectors, sealing compounds, and enclosures. When making connections, ensure that all wires are properly stripped and crimped or screwed into the connectors. Apply a generous amount of sealing compound to the connections to create a watertight seal. In addition, the panel enclosure itself should be watertight to prevent moisture from entering the enclosure. Fourthly, the remote panel should be installed in a moisture-proof enclosure to prevent condensation and moisture buildup. Moisture can damage electrical components and lead to corrosion, short circuits, and other electrical problems. A moisture-proof enclosure is designed to protect the electrical components from moisture and condensation. These enclosures are typically made of non-corrosive materials such as fiberglass or plastic, and they are designed to be watertight. When selecting a moisture-proof enclosure, ensure that it is appropriately sized for the electrical components that will be housed within it. The enclosure should also be properly ventilated to prevent heat buildup. Fifthly, provide adequate ventilation in the remote panel to prevent overheating. Electrical components generate heat as they operate, and if this heat is not properly dissipated, it can lead to overheating and premature failure. Adequate ventilation helps to remove heat from the enclosure and maintain a safe operating temperature. Ventilation can be achieved by using vents, louvers, or fans. The size and number of vents or fans will depend on the amount of heat generated by the electrical components. When designing the ventilation system, consider the ambient temperature and humidity of the environment. In hot and humid climates, more ventilation may be required. Sixthly, clearly label the remote panel as such and indicate the location of the main service panel. This is important for safety and convenience. Labeling the remote panel helps to identify it as a separate electrical system and prevents confusion during maintenance or repairs. The label should clearly state that the panel is a remote subpanel and indicate the location of the main service panel. This information can be crucial in the event of an emergency, as it allows electricians or other personnel to quickly locate the main service panel and disconnect power to the remote subpanel. In summary, when installing a remote subpanel, it's essential to follow all applicable codes and regulations to ensure safety and compliance. This includes adhering to the NEC requirements for underground feeder cable depth, grounding, conduit length, connectors, watertight connections, moisture protection, ventilation, and labeling. By paying attention to these details, you can create a safe and reliable electrical system for your remote outbuilding. Now let's elaborate on the grounding electrode system and its components. The grounding electrode system is a critical part of any electrical system, as it provides a path for fault current to flow back to the source. This allows the overcurrent protection device to trip and to energize the circuit, preventing electrical shock and minimizing the risk of fire. As mentioned, the grounding electrode system typically consists of a ground rod, buried pipe, or plate electrode. A ground rod is a metal rod that is driven into the ground. The rod is typically made of copper or copper-clad steel, and it should be at least 8 feet long. The ground rod should be driven into the ground until at least 8 feet of the rod is in contact with the earth. A buried pipe is a metal pipe that is buried in the ground. The pipe should be made of galvanized steel or copper, and it should be at least 10 feet long. The pipe should be buried at least 2.5 feet below the surface of the earth. A plate electrode is a metal plate that is buried in the ground. The plate should be made of copper or galvanized steel, and it should be at least 2 feet square. The plate should be buried at least 2.5 feet below the surface of the earth. The choice of grounding electrode will depend on the soil conditions and local requirements. In general, a ground rod is the most common and cost-effective option. However, in areas with poor soil conductivity, a buried pipe or plate electrode may be necessary to achieve adequate grounding. Once the grounding electrode is installed, it should be connected to the panel enclosure using a grounding conductor of the appropriate size. The size of the grounding conductor is determined by the size of the feeder conductor supplying the subpanel. The grounding conductor should be connected to the grounding busbar within the subpanel enclosure. The grounding busbar is a metal bar that is used to connect all of the grounding conductors together. The grounding busbar should be securely mounted to the panel enclosure. In addition to the grounding electrode system, it's also important to bond all metallic components together. This includes metal conduits, metal enclosures, and metal equipment. Bonding these components together ensures that they are all at the same electrical potential. This helps to prevent electrical shock in the event of a fault. Bonding can be achieved by using bonding jumpers. A bonding jumper is a short length of wire that is used to connect two metallic components together. The bonding jumper should be sized appropriately for the size of the conductors supplying the equipment. All bonding jumpers should be securely fastened to the metallic components. Another important consideration is the separation of the neutral and grounding conductors at the subpanel. As mentioned, the neutral conductor should only be connected to the grounding busbar at the main service panel. At the subpanel, the neutral conductor should be isolated from the enclosure and the grounding busbar. This prevents objectionable current from flowing on the grounding conductors. Objectionable current is current that flows on the grounding conductors due to improper wiring or equipment faults. This current can cause the grounding conductors to heat up, which can create a fire hazard. To prevent objectionable current, it's important to follow the NEC requirements for separating the neutral and grounding conductors. Now let's discuss the specifics of selecting and installing underground connectors. Underground connectors are designed to provide a reliable and watertight connection in underground applications. These connectors are typically made of corrosion-resistant materials such as copper or stainless steel, and they are designed to withstand the harsh conditions of underground environments. When selecting underground connectors, it's important to choose connectors that are specifically listed and labeled for underground use. These connectors have been tested and certified to meet the requirements of the NEC and other applicable standards. There are several different types of underground connectors available, including compression connectors, bolted connectors, and heat shrink connectors. Compression connectors are crimped onto the conductors using a special crimping tool. Bolted connectors are bolted together using bolts and nuts. Heat shrink connectors are covered with a heat shrink tubing that shrinks when heated, creating a watertight seal. The choice of connector will depend on the size and type of conductors being connected, as well as the specific application. When installing underground connectors, follow the manufacturer's instructions carefully to ensure proper and reliable connection. Firstly, strip the insulation from the conductors to the appropriate length. Secondly, clean the conductors to remove any dirt or corrosion. Thirdly, apply an antioxidant compound to the conductors. Fourthly, insert the conductors into the connector. Fifthly, crimp or bolt the connector together according to the manufacturer's instructions. Sixthly, if using a heat shrink connector, slide the heat shrink tubing over the connector and heat it with a heat gun until it shrinks and creates a watertight seal. Seventhly, inspect the connection to ensure that it is secure and watertight. In addition to using the correct connectors, it's also important to protect the connections from physical damage. This can be achieved by burying the connections deep enough to prevent them from being damaged by digging or other activities. The connections can also be protected by encasing them in concrete or other protective materials. Remember that maintaining watertight connections is vital for the longevity and safety of the electrical system. Moisture intrusion can lead to corrosion, short circuits, and ultimately, system failure. As such, regular inspections and maintenance are recommended to ensure the integrity of these connections. Speaking of moisture, let's elaborate on the importance of moisture protection for the remote panel. Moisture is a major threat to electrical systems, as it can cause corrosion, short circuits, and other electrical problems. In remote outbuildings, where the panel may be exposed to the element, moisture protection is especially important. As mentioned, The remote panel should be installed in a moisture-proof enclosure to prevent condensation and moisture buildup. These enclosures are typically made of non-corrosive materials such as fiberglass or plastic, and they are designed to be watertight. When selecting a moisture-proof enclosure, ensure that it is appropriately sized for the electrical components that will be housed within it. The enclosure should also be properly ventilated to prevent heat buildup. In addition to using a moisture-proof enclosure, there are other steps that can be taken to protect the panel from moisture. Firstly, seal all openings in the enclosure with a watertight sealant. This includes openings for conduits, wires, and other components. Secondly, install a drip loop in the wires entering the enclosure. A drip loop is a loop of wire that hangs below the entrance to the enclosure. This loop allows any water that runs down the wire to drip off before it enters the enclosure. Thirdly, consider using a desiccant to absorb any moisture that may enter the enclosure. A desiccant is a substance that absorbs moisture from the air. Desiccants are available in various forms, such as packets or cartridges. The desiccant should be placed inside the enclosure and replaced periodically. Fourthly, inspect the enclosure regularly for signs of moisture. If any moisture is found, take steps to eliminate the source of the moisture and dry out the enclosure. Fifthly, apply a corrosion inhibitor to all electrical connections. A corrosion inhibitor is a chemical that prevents corrosion from forming on metal surfaces. Corrosion inhibitors are available in various forms, such as sprays or pastes. The corrosion inhibitor should be applied to all electrical connections before they are made. In addition to protecting the panel from external sources of moisture, it's also important to prevent condensation from forming inside the enclosure. Condensation can occur when warm, moist air comes into contact with a cold surface. To prevent condensation, ensure that the enclosure is properly ventilated. Ventilation allows warm, moist air to escape from the enclosure, preventing it from condensing on the cold surfaces. The ventilation system should be designed to provide adequate airflow without allowing moisture to enter the enclosure. Moving on, let's detail the importance of ventilation in the remote panel to prevent overheating. Overheating can damage electrical components and lead to premature failure. Adequate ventilation helps to remove heat from the enclosure and maintain a safe operating temperature. Ventilation can be achieved by using vents, louvers, or fans. Vents are openings in the enclosure that allow air to flow in and out. Louvers are angled blades that are installed in the vents to prevent rain and snow from entering the enclosure. Fans are used to force air through the enclosure. The size and number of vents or fans will depend on the amount of heat generated by the electrical components. When designing the ventilation system, consider the ambient temperature and humidity of the environment. In hot and humid climates, more ventilation may be required. The ventilation system should be designed to provide adequate airflow without allowing moisture to enter the enclosure. Vents and louvers should be positioned to prevent rain and snow from entering the enclosure. Fans should be positioned to exhaust hot air from the top of the enclosure and draw cool air in from the bottom of the enclosure. The ventilation system should be inspected regularly to ensure that it is functioning properly. Vents and louvers should be cleaned periodically to remove any dirt or debris that may be blocking airflow. Fans should be inspected for proper operation and replaced if necessary. In addition to providing ventilation, it's also important to avoid overcrowding the enclosure. Overcrowding can restrict airflow and cause heat to build up inside the enclosure. Ensure that there is adequate space around all electrical components to allow for proper ventilation. Remember that maintaining a safe operating temperature is crucial for the reliability and longevity of the electrical system. While providing adequate ventilation, you can prevent overheating and ensure that the electrical components operate within their safe temperature limits. Finally, let's discuss the importance of labeling the remote panel and indicating the location of the main service panel. Clear and accurate labeling is essential for safety and convenience. Labeling the remote panel helps to identify it as a separate electrical system and prevents confusion during maintenance or repairs. The label should clearly state that the panel is a remote subpanel and indicate the location of the main service panel. This information can be crucial in the event of an emergency, as it allows electricians or other personnel to quickly locate the main service panel and disconnect power to the remote subpanel. The label should be made of durable material that is resistant to weathering and fading. The label should be securely attached to the panel enclosure in a visible location. In addition to labeling the remote panel, it's also important to label the circuits within the panel. Each circuit breaker or fuse should be labeled with a description of the circuit that it protects. This helps to identify the correct circuit when troubleshooting or making repairs. The circuit labels should be clear and easy to read. They should be made of durable material that is resistant to fading. The circuit label should be securely attached to the panel enclosure next to the corresponding circuit breaker or fuse. Another important aspect of labeling is to indicate the voltage and amperage of the panel. This information is important for ensuring that the panel is properly loaded and that the correct overcurrent protection devices are used. The voltage and amperage rating should be clearly marked in the panel enclosure. In addition to labeling the panel itself, it's also important to provide documentation about the electrical system. This documentation should include a wiring diagram, a list of circuits, and a description of the grounding system. The documentation should be kept in a safe and accessible location. It should be updated whenever changes are made to the electrical system. Remember that clear and accurate labeling is an essential part of a safe and well-maintained electrical system. By taking the time to properly label the remote panel and the circuits within it, you can help to prevent confusion and ensure the safety of yourself and others. Let's synthesize all the key takeaways to ensure a comprehensive understanding of remote subpanel installations. Firstly, always adhere to NEC section 300.5, ensuring a minimum burial depth of 18 inches for underground feeder cables, reducing it to 6 inches only when cables are under protective slabs or pavement. Secondly, establish a robust grounding system at the remote subpanel, mirroring requirements for any subpanel inside a building. This includes installing a grounding electrode system, such as a ground rod, and connecting it to the panel enclosure using a correctly sized grounding conductor. Thirdly, keep the underground conduit for the feeder cable limited to a maximum length of 10 feet to mitigate condensation risk. Fourthly, insist on using connectors specifically approved and designed for underground use to combat moisture and corrosion. Fifthly, ensure that every electrical connection within the remote panel is completely watertight, employing sealing compounds and appropriate connectors. Sixthly, house the remote panel within a moisture-proof enclosure to proactively defend against condensation and moisture accumulation. Seventhly, implement adequate ventilation strategies within the remote panel to prevent any potential overheating of component. Eighthly, meticulously label the remote panel, clearly marking it as such and explicitly indicating the location of the main service panel for safety and ease of identification. Ninthly, remember the importance of separating the neutral and grounding conductors correctly, only connecting the neutral conductor to the grounding busbar at the main service panel and isolating it at the subpanel to prevent objectionable current. Tenthly, perform regular inspections and maintenance of all connections, enclosures, and ventilation systems to ensure ongoing safety and reliability. By meticulously addressing each of these key points, one can confidently ensure a remote subpanel installation that is not only safe and compliant but also reliable and long-lasting. The combination of proper grounding, protection from the elements, and clear labeling contribute to a system that is easy to maintain and troubleshoot, reducing the risk of electrical hazards and ensuring the consistent operation of the electrical supply to the remote outbuilding.